NASA's Jet Propulsion Laboratory presents the Von Kármán Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Good, excellent. Well, thanks for joining us for our final edition for the 2014 series. We're back in January, though, so the schedule's on our website, so don't miss out. Make sure you take a look. The ambitious and exciting Dawn mission is one of NASA's most remarkable ventures into the solar system. After more than 7 years of interplanetary spaceflight and a spectacular exploration of Vesta, the probe is just a few months away from the mysterious world Ceres. These objects, the two most massive residents of the main asteroid belt, were among the last uncharted worlds in the inner solar system prior to Dawn. Ceres is so large that it is included in the category of dwarf planets, along with Pluto. Remnants from the time that planets were formed, Ceres and Vesta hold clues that will help scientists understand the dawn of the solar system. Dawn orbited Vesta from July 2011 to September 2012 and returned astonishing views of this fascinating world. It is the only spaceship ever to orbit an object in the asteroid belt and is the first ever targeted to orbit any two extraterrestrial destinations. Tonight's guest will give a fascinating and entertaining presentation on the Dawn mission and its two exotic destinations, as well as on its use of ion propulsion. He will share the excitement and profundity of controlling a robotic ambassador from Earth in deep space. Tonight's guest grew up in Toledo, Ohio. He earned his AB in physics at Princeton University, an MS in physics at the University of Colorado in Boulder, and a PhD in physics at the Joint Institute for Laboratory Astrophysics. He combined his scientific training with his lifelong study and passion for the exploration of space by joining JPL in 1986. His work there has spanned a broad range, including missions to detect planets around other stars, design of a mission to return samples from Mars, a laser altimeter for Mars, the development of systems to use lasers instead of radios to communicate with spacecraft, and much, much more. Of note is the Deep Space One mission, the first of the new Millennium program, designed to test exotic and risky technologies by flying them on dedicated flights. DS-1, as it's called, tested technologies like ion propulsion and artificial intelligence and was extremely successful. Our guest worked on that project from its inception and served as chief mission engineer, mission director, and project manager. Now he is the chief engineer and mission director on Dawn, which uses some of those very same technologies. He is also very active in education and public outreach and is a very popular public speaker. You'll see why tonight. He's received numerous awards from both JPL and NASA, is an avid collector of all manner of space memorabilia, and amongst other things, he has a black belt in karate. I could seriously go on, but we'd be here all night. So, ladies and gentlemen, please help me welcome tonight's guest, Dr. Marc Rayman.
Thank you, Mark. That's very nice. Thank you very much. I appreciate your interest, and thanks for coming, and welcome to people who are watching on the web. So I'm going to tell you about the Dawn mission, and as you know, this is a NASA mission. We're here at JPL, which is run by Caltech for NASA, but there are many organizations around the country and indeed around the world involved in this project. But before I tell you about Dawn, I want to give you a little bit of context, so take you back in time and talk about what astronomers knew about the solar system in 1800. And so here's a sort of conventional view of the solar system where we're looking down on it with the sun in the center, and here are the orbits of the inner planets. Here's the orbit of Earth, Mars, Jupiter, Saturn, and Uranus. And this is pretty much what astronomers knew about the contents of the solar system in 1800. And in fact, even this was a new picture because Uranus had only been discovered in 1781. So this same picture could not have been drawn 20 years earlier. Of course, the planets from Mercury to Saturn were known even to ancient astronomers. But apart from some moons of these planets and occasional comets, this is pretty much what astronomers knew in 1800. Now, for fun, although these are the contents of the solar system in 1800, I'm showing you their locations today on December 4th, 2014, which is why if you're here on Earth, which everybody is in the room, people here on the web, I'm not sure where you are, but if you're here on Earth and you imagine Earth rotating this way, that is counterclockwise, you can see that after the sun goes down, Mars follows it, not too much afterwards, which is why maybe you're seeing Mars in the evening skies these days. And later in the night, as Earth continues to rotate, Jupiter is up in the constellation Leo. Okay, now, again, this is what astronomers knew in 1800. Then along came this fellow, Giuseppe Piazzi, a mathematician and astronomer, and he got the new year off to a good start. He discovered a new planet. I mean, modern astronomers had only ever discovered one planet. That was Uranus, and so this was quite a significant finding. And I'm going to show you a high-resolution photograph of what Mr. Piazzi discovered. That's here. She's Ceres, the goddess of agriculture and grain. And Ceres is often depicted with her harvest bounty here and her crown of grains and her, in this case, scythe, although different artistic impressions of Ceres will use different farming implements, but that's a matter of the choice of the artist. But if you had cereal this morning, then you owe a debt of at least etymological gratitude to Ceres. So this is what Mr. Piazzi discovered. And now this is the same chart I showed you just a moment ago, the planets as they were known in 1800. And this is the planets as they were known in 1801. And so Ceres fit very nicely into this gap between Mars and Jupiter, and for much of the next nearly half century was considered to be a planet. Now, that makes a nice story, and it actually happens to be true. But then along came this fellow, Heinrich Wilhelm Olbers, who the very next year discovered another new member of the solar system family. But more importantly, for what I want to tell you about the dawn story, in 1807, he discovered still another new member of the solar system family between Mars and Jupiter, what by then was the fourth addition. And I'll show you I should also mention, actually, Olbers was actually just an amateur astronomer. He was trained as a physician, but was fantastically productive in astronomy. And many amateur astronomers, perhaps even today, remember his name or know his name. There's the Olbers paradox, and he made many important contributions. But let's see what he discovered. That's here. She's Vesta, the goddess of hearth, home, and family. Now, it's interesting. Vesta is rarely depicted in art. But when she is, she often has this very stern look on her face. But I hope to convince you this evening that the solar system body, Vesta, is a much happier place. And the way she figures into the Roman mythology is not as well understood as it is for many other of the gods and goddesses, because she was worshipped privately in the home. And so there are fewer surviving records of exactly how she fit in. Now, you've undoubtedly heard of the Vestal virgins who are connected with her, but I'm speaking of Vesta, the goddess herself. But again, this is what the nice Dr. Olbers discovered. And now here, I've zoomed in a little bit, so now Jupiter is the outermost planet. And now you can see both Vesta and Ceres fit nicely into this space between Mars and Jupiter. And once again, I'm showing you their locations today, December 4th, 2014. So now that we're looking in a little more closely, you can see that if you're here on Earth, this is not a good time to see Mercury because of how close it is to the sun, but Venus is just starting to show up in the, or not, shouldn't say just starting, but is still just showing up in the evening skies. So Vesta and Ceres and these other bodies, for, again, much of the first half of the 19th century were considered to be planets. But then science and technology advanced, and eventually more and more and more bodies started to be discovered in the solar system, in this part of the solar system, until now it's looking something more like this. And for those of you who are sitting in the front row, I will invite you to confirm for the people who are sitting in the back that I've added 10,320 individual dots to this chart. And those of you who are watching on the web, this is the time to pause and count them to show that number of asteroids today. Now, we know about many, many more asteroids than that. I'm only showing you the ones that are larger than about 5 miles or so across. But what this shows us is this part of the solar system, which we now call the asteroid belt, is very different from the inner solar system, which is largely devoid of these bodies. And in fact, if we zoom out, you can see even more clearly that there's something different about this part of the solar system from in here and out here. Something different. And so that raises the question, why is that? Why is this part of the solar system different? Well, you're a great audience for asking that question. I appreciate it, because the next part of my presentation is going to be to give you an idea of what the answer is. But to do that, I have to take you back in time a little bit to before Piazzi's 1801 discovery of Ceres. In fact, I have to take you back to the dawn of the solar system. Get it? I'm telling you about the Dawn mission. Okay. So this is a photograph from the Hubble Space Telescope of something in the constellation Sagittarius, part of the Trifid Nebula, which perhaps you've seen yourself if you're an amateur astronomer, although you probably haven't had as good a view as Hubble did. And what we're seeing here is a large interstellar cloud of gas and dust. And off the top of the picture, up here, out of Hubble's view, is a brilliant star. And the light of this star is so intense that as it shines down on this cloud, it's virtually blowing this material away in space. So it's almost as if it's evaporating it here. Yet right here, there's a knot of material so dense that it's blocking the light of the star and preventing it from eroding the material here. So that's why this extra gas and dust is sticking out of the cloud like a finger. And deep inside here are conditions that we believe are very much like those that gave rise to our solar system 4.6 billion years ago. Because that material is starting to collapse under its own weight. And eventually, it will collapse to the point that it forms a star. And then when it forms a star, we can begin to form planets. Because now we have this swirling cloud of debris. Particles are flying around, and sometimes these particles will hit. Now, sometimes when they hit, they'll break apart. Other times, however, particles will hit and stick together. And we can see that happening right here, where two particles stick, and then another particle, and another particle, and another particle. And these particles, as they stick, they build up. They grow larger and larger and larger. Now, on the chart, they're growing larger to form words, but in space, they grow larger to form rocks. And those rocks eventually will grow still larger to form planets. And we believe that's how the rocky planets of the inner solar system, one of which is right under our feet, formed about 4.6 billion years ago. However, when massive Jupiter formed, it interrupted this process and terminated the growth of the material there into planets. And so what's left is this belt of asteroids. And Ceres and Vesta are sometimes called protoplanets because they were in the process of growing to become full-size planets when Jupiter deprived them of the opportunity to continue growing. And Dawn's mission is to fly out to the asteroid belt and study these bodies. And these are the two most massive residents of the main asteroid belt. So let's summarize the motivation for the mission. We want to explore Ceres and Vesta in order to get insights into the conditions and the processes that were acting at the dawn of the solar system. Okay. That's the motivation for the mission. Now, I think when most people think of asteroids, they think of chips of rock, right? The size of buildings, like maybe the size of this building, or mountains, and that's how they're often depicted in movies, right? But Vesta, in particular, is not like that. Here's a view to scale of Vesta and other asteroids that spacecraft have visited. And you can see Vesta, with an equatorial diameter of 350 miles, is much larger. It really is different from these other chips of rock. And Ceres is much larger still. Indeed, Ceres is the largest body between the Sun and Pluto that a spacecraft has not yet visited. So these really are of a different scale. And so let's have another look at that. Here again are Vesta with its equatorial diameter of 350 miles, and Ceres an equatorial diameter of 600 miles. So we can compare them again with the two largest asteroids that had been visited prior to the Dawn mission. We see these are different, so we can put them in the context of other objects in the solar system that you may be familiar with. And what this shows us is these really are not like typical asteroids. And in fact, you heard from Mark in that very nice introduction that Ceres is included in the same category of dwarf planets as Pluto. I'm sure most of you remember in 2006 when Pluto was recategorized from being a planet to a dwarf planet, and oh my goodness, everybody thought this was awful. How could Earth be so inconsiderate, and why didn't we account for Pluto's feelings in this matter? And just we should have been more sensitive. Well, whatever you think of that decision, at the time that decision was made, Ceres fit into the same category. So it was the first dwarf planet discovered 129 years before Pluto. So what this shows me is that Vesta and Ceres really are whole worlds. And one of the things that I think is so cool about a mission like this is we're truly exploring some of the last uncharted worlds in the inner solar system. I think that is really cool. Now, when you look at a picture like this, it's deceptive because California is flat, right? But these are round, three-dimensional bodies. And so you wouldn't compare them any more than you would compare a piece of paper to a basketball, right? These have much more area than is suggested in a picture like this. In fact, Vesta has about twice the surface area of California. So we can go into the third dimension, where here I've got a Hubble Space Telescope map of the surface of Ceres, and as is often the case in these astronomical photographs, the color doesn't tell you anything about the color of Ceres. This is encoding some other scientific information, which doesn't matter for these purposes. And Hubble couldn't see all the way to the North Pole and all the way to the South Pole, which is why that's black. But the white rectangle I've drawn around it shows the surface area of Ceres on the same scale as the surface area of the continental United States. And sure, Ceres isn't as big as the United States. Ceres isn't as big as Earth. But it's still a big place. It's 38% of the area of the continental United States. And if you just think about how vast and varied and frankly beautiful the geography and topography of our country are, it suggests there's an opportunity on a place like Ceres for a lot of diversity, a lot of different things to see. And again, that to me is what's so cool about sending a spacecraft there to learn more about it. This is a big place. So let's take a more careful look at it. Here it is in a set of Hubble Space Telescope images, and you can't really see a whole lot. If you have a good imagination and a pure heart, you may see some features as they move across the surface. But mostly all you really can see is it's sort of round and it's sort of planet-like, and that's really about it. Because powerful as Hubble is, Ceres is still far away and not all that large. So we have to resort to an artist's concept. And unfortunately, if my computer would cooperate, oh, sorry, that's not what you're supposed to see. Instead, what I want you to see is that it's believed that Ceres is covered with a thin, dusty crust. And if we take advantage of the artistry to look inside, it's thought that it may have a thick, rocky core, and perhaps between them, a layer of water ice, perhaps even with liquid water. So this raises a very intriguing possibility that Ceres may have subsurface reservoirs of liquid water. And the opportunity now to send a spacecraft to this distant body to try to determine whether or not indeed there's water under the surface, I think is really, again, an exciting possibility. And so we don't know what Ceres will look like when we get there, but it may show evidence even on the surface of some interactions between the surface and these subsurface reservoirs of water. And in fact, it was reported earlier this year that a really remarkable spacecraft, the Herschel Space Observatory, operated by the European Space Agency, detected water vapor in the space above Ceres. Now, very, very tenuous to be sure. Indeed, the density of the water vapor is lower than the density of Earth's atmosphere 100 miles above the space station. So we're not going to be seeing fountains there. Nevertheless, the fact that there's water vapor in the space above Ceres provides a really tantalizing clue that there will be something cool there to find out about. And we're on the verge of getting there to see what there is to learn. But now, again, you can't really see much with these pictures. Here, again, is this Hubble Space Telescope photograph, and we just don't have the resolution from this great distance to see it in detail, which of course is the reason for sending a spacecraft there. And in fact, just next month, in January, we will be getting pictures from Dawn that are beginning to exceed the quality of Hubble. And by February, we'll be getting pictures that are substantially better than Hubble. And then they will only get better after that. But I don't have any of those yet. But I want to at least illustrate the power of increasing resolution. So here's a pixelated image. And if we think of this as the resolution of the Hubble picture, then you can begin to imagine that as you get better and better and better resolution, the secrets that are hidden in this picture begin to become evident. And it's just really almost impossible to imagine what you might find when the picture really is revealed. And that change in resolution that I just showed you is the improvement in performance that Dawn will achieve from what Hubble got over the course of this next calendar year. But let's get rid of that and move on to something else. So now here's a Hubble Space Telescope view of Vesta. And if we take a look at it starting here and follow the shape like this, it's looking pretty much planet-like. Even a little bit of flattening at the North Pole, and many planets, including yours, is a little flattened at the North Pole. But as we come around here, you would expect the shape here to be smoother, right? You'd expect it to look a little bit more like this. But when astronomers got these Hubble pictures at the end of the 1990s, they recognized that that's indeed not what's seen, and determined that probably what we're seeing here is a large crater with a mountain in the center. And maybe you've seen pictures of craters on Mars or the Moon. Big craters often have mountains in the center. And the reason for that is the way you make a crater like that is you take a big piece of interplanetary debris, and it comes screaming down into the surface, and it hits the surface with so much energy that the rock virtually melts, and it flows away from the impact, and then it sloshes back. And as it sloshes back, it solidifies. And so that mountain in the center of a crater is like a snapshot of the process by which that crater was formed. And so I want to show you an artist's concept of the formation of this crater. So here's a big piece of interplanetary debris early in the history of the solar system. There's Vesta before the impact, and there's Vesta after the impact. And when it hit, it sprayed a huge amount of material out into space. And some of those rocks went on their own independent orbits around the sun, and some of them may have made their way to the part of the solar system where you spend most of your time. And as you know, if you're lucky enough to be out on a nice dark night and you see a meteor, you may be seeing a piece of interplanetary debris burning up in the atmosphere. And in fact, if you've seen that, maybe you've seen a piece of Vesta burning up in the atmosphere. Now, when I say that, I'm not just being poetical or clever, but I am poetical and clever. I'm being serious because it's been determined with data from the Dawn mission that about 6%, I mean, think of this, 1 in 16 meteorites seen to fall on Earth may have come from that one impact at Vesta, probably more than 1 billion years ago. Now, you probably know we have meteorites from Mars, and maybe you know we have meteorites from the Moon. But we have far, far, far more meteorites from Vesta than we do from the Moon or Mars. And those are the only 3 solar system bodies to which we have linked specific meteorites. So this really presents an exciting opportunity to have been able to study these things in the laboratory for decades, and now to have a spacecraft there visiting them. And this is one of these meteorites. These are very common. I took this picture myself in a museum, but these are all over the place. In fact, one of them fell and landed in this box here. And after the talk, if you're interested, you can come up and see it. I just bought this myself, even years before I was involved in the Dawn mission, just because I thought it'd be neat to have a piece of Vesta. And you can come up and take a look at this if you're interested. So that's the meteorite story, but let's get back to Vesta itself. So here again is Vesta in the best view we had prior to the Dawn mission. And then this is what Dawn showed us. And of course, we zoomed in even more and then got to see something more like this. And so here is that huge crater near the South Pole. This crater is 300 miles in diameter. This is a big place. And this is one of the first features that we noticed. And in fact, a friend and colleague of mine who's sitting right here nicknamed that the snowman, and that became a very popular term, and you can see why. And I'll show you a better view of that a little bit later on. But while Dawn was in orbit for 14 months, we took 31,000 pictures. And unfortunately, it looks like I don't have time to show all of them to you. So instead, what we'll do is put them together into a view that you would have if you were actually there. So these are based on our pictures, and we're starting here in the northern hemisphere. And one of the first things you'll notice is the northern hemisphere is much more densely cratered than the southern hemisphere. Why is that? Because this big impact at the South Pole, near the South Pole, deposited so much debris over the surface that it erased the record of cratering, and then new bodies had to fall in to create new craters. There's a set of chasms, canyons, near the equator, I'll show you some more views later, that are a result of the disruption of this body from this giant impact. More than 90 of these canyons that rivaled the Grand Canyon in size. Here now we're seeing into the crater. This is the mountain in the center of the crater. This is part of the crater wall. Much of it's been destroyed excuse me, over the subsequent hundreds and hundreds of millions of years, but some of it still survives to show this truly remarkable view of the second most massive body in the main asteroid belt, which prior to a few years ago had only been glimpsed telescopically for centuries. Now, I included this picture because, to be perfectly honest, I just happen to think it's a really neat view. So here again is this snowman triplet of craters. And for scale, this is about, a little bit more than 40 miles across or so. And here are some of the the chasms that are running along the equator. And again, these were caused by the powerful impact near the South Pole. So much energy reverberated through Ceres that it almost destroyed, through Vesta, that it almost destroyed the body. Fortunately, it didn't, otherwise we wouldn't have had a place to send the spacecraft, but it left these tremendous scars. And here also you can see the border between the heavily cratered northern part of Vesta and the more gently cratered, lightly cratered southern hemisphere. And when you go to a new place, you have to start naming things, and we've named many of the features there, and the craters are named for the Vestal Virgins and other famous Roman women, and other features, mountains and canyons, and other features are named for towns and festivals associated with the Vestals. Now, I included this picture because the animation and the other photographs that I've shown you, and this one, have all been in black and white. But of course, Dawn has many sensors on it, and so they allow us to see other information that isn't captured in a black and white picture. Now, just like the photograph from Hubble of Ceres that I showed you earlier, this isn't the way it would look to your eye, but it shows you that we can use this so-called false color with the sensors that we have on board to bring out other information there. And so you can see that perhaps what we're seeing is that this crater was formed by an object traveling like this. It hit here and then sprayed out this orange material, and you can see something of different composition here and down here and some other things up here. And so what it shows is there's a very complex and diverse geology on this body. It's not just a chunk of rock. Now, in this case, using the color not to show you something about the composition, but rather the elevation. So what we're seeing here is the entire southern hemisphere sort of unwrapped, if you will. So this is the equator all the way around. South Pole is near here. And this is the scale for the color. So I don't know how well you can read it on the web, but what it's showing is the deep blue is 14 miles below in elevation, and the white is 12 miles above. Of course, there's no sea level, obviously, on Vesta, but there's a standard reference. And we can put that into scale by comparing that here with the size of Mount Everest. So this shows that the topography on Vesta is entirely unlike what you have on your planet. This mountain in the center here is about 2.5 times the height of Mount Everest relative to these surrounding plains here. And the walls of the crater rim here rise to nearly 3 times the height of Mount Everest. This is truly extraordinary. And this is now about the second tallest mountain that we know in the solar system. And the only one that's higher, Olympus Mons on Mars, is only a little higher. But nothing like this on Earth. And if you just imagine standing inside this crater, 300 miles in diameter, a mountain more than 100 miles across at the base, soaring to 2.5 times the height of Mount Everest, with crater walls rising even higher than that. Excuse me, what an extraordinary view this would be. This is truly an exotic alien world. So that's just a little bit of an overview of Vesta. But I want to give you an overview of the entire mission. And so we started from most people's favorite planet, Earth. We launched in September 2007. And we started out with a big rocket. I threw that in just to help keep you awake. But on our way out to the asteroid belt, we flew by Mars and robbed it of some of its orbital energy around the sun in order to help fling the spacecraft to more distant and more difficult to reach targets. And in the process of doing that, we actually slowed Mars down in its orbit in exchange for speeding the spacecraft up. And so for those of you who are keeping track of this sort of thing, Mars now travels more slowly at the rate of about 1 inch per 180 million years. And I'm sure on behalf of everyone on Earth, we appreciate Mars' contribution to the Dawn mission. So then in July of 2011, we got to Vesta and went into orbit around it. We didn't just fly by, as many spacecraft have at asteroids. We went into orbit and spent 14 months there scrutinizing this body. And then we broke out of orbit, and the spacecraft is now on its way to Ceres. And you can see we will get into orbit in just a very few months. Just about 3 months from now, on March 6th, we will arrive in orbit. And at each target, we make a comprehensive set of measurements. We take photographs of the surface, and we're all visual creatures, right? You like to see cool pictures, and we do too. So we fully photograph the surface. We also take pictures in stereo, different angles, in order to make a topographical map, which is how I was able to tell you how tall the mountains are and how deep the chasms are and things like that. Excuse me. We also have sensors that let us map the elemental composition. That is, what are the atomic constituents of these bodies? And we map the mineralogical composition. That is, what kind of rocks are there? How do these atoms combine to form minerals? We measure the gravity field because that tells us about the interior structure of these bodies. And so, for example, at Vesta, scientists were able to determine that it has a dense iron-nickel core, somewhat like Earth does. Now, of course, Earth's core is molten. The core of Vesta is no longer molten. It likely was at some time. But the point is, it isn't just another chunk of rock. It's really more like a mini planet. And we searched for moons because certainly Vesta and Ceres were large enough that they could have moons of their own. We didn't find any at Vesta, but we conducted a thorough search. And starting next month, our images will contribute to our search for moons around Ceres. So this is not only the only spacecraft ever to have orbited an object in the main asteroid belt. No spacecraft had ever orbited one prior to Dawn orbiting Vesta. But there's an interesting point here. This is the only spacecraft ever to orbit any 2 extraterrestrial destinations. Now, when you think about it, that's kind of a funny thing. I mean, in 57 years of space exploration, no spacecraft has ever attempted to orbit 2 different solar system targets. Seems like a pretty obvious kind of thing to do, right? Go to one place, linger there for a long enough time to really capture all the information that you want, and then leave orbit and go someplace else and do the same thing. Yet it's never even been attempted before. It's not as if nobody ever thought of it, right? It happens in science fiction all the time. Go to some planet, do whatever you're going to do there, beat somebody up or make out with them, and then go to some other solar system destination and do the same thing there. And yet it's never been tried before. And that raises the question, why is that? Why have we never done that before? Well, once again, thank you for asking that question. The reason is because until recently, engineers were confronted with a problem. And they were confronted with the same problem as these two fellows. That is, we just haven't had the technology to carry it out. It turns out that a mission to orbit two different solar system destinations is far, far, far beyond the capability of conventional chemical propulsion. And so a few years ago, a number of us at JPL got together and asked the question, how can we travel around the solar system more easily and less expensively? And our answer to that was ion propulsion. Now, if you're like me, and I know at least some of you are, the first time you ever even heard of ion propulsion was in science fiction. In fact, the first time I ever heard of it was in a Star Trek episode where Kirk, Scotty, and Spock talk about how impressive ion propulsion is. And here it is in Star Wars. So you recognize the Star Wars TIE fighter that Darth Vader and the evil Empire used against Luke Skywalker and the members of the Rebel Alliance. And in the Star Wars universe, the TIE fighter, TIE, stood for Twin Ion Engine, because this was one of the most futuristic, coolest, most advanced technologies George Lucas could think of. And to me, one of the things that's really cool about working on a project like this is getting to turn that science fiction into science fact. So this is the fact of ion propulsion. And I won't spend a great deal of time on this, but just to give you an idea, the way it works is we start with the gas xenon, which is like helium or neon, but heavier, and we introduce it into a chamber here in an engine that's about 1 foot in diameter. And we bombard these xenon atoms with electrons to give them a little electric charge. When they get a little electric charge, they're called ions. And these ions then, like any charged object, can feel the effect of a voltage. And so we have a metal grid right here and another one right here, two grids very close together. They're separated by only about 10 times the thickness of your hair, or 20 times the thickness of my hair. We put a large voltage between them, and we accelerate these xenon ions to the right. And the action of an ion going to the right causes a reaction that pushes the spacecraft to the left. And because we shoot these ions out at such high velocity, 90,000 miles per hour, each one imparts a relatively large push back on the spacecraft. And so this system is very, very efficient. It's 10 times as efficient as conventional chemical propulsion, which means we can undertake much, much more ambitious missions. This would be like having your car get 300 miles per gallon. This is a photograph of an ion engine operating in a vacuum chamber here at JPL, where all of us are, just a few hundred yards from here. And you can see it really does produce the cool blue glow like in science fiction movies. And the reason for that is xenon just happens to glow blue like neon just happens to glow orange. Now, while this system is very, very efficient, we only flow a small amount of xenon through the engine at a time. In fact, it would take Dawn 2 days to expend just 1 pound of propellant. So it's efficient, but the thrust is very gentle. And in fact, I'm going to do an ion propulsion experiment here in front of you. Usually this works, and this is pretty safe, so you can do this at home. You can do it here on the web. And that is, the ion engine pushes on the spacecraft as hard as this piece of paper pushes on my hand. And yet, in the zero-gravity, frictionless environment of space, gradually the effect of this thrust can build up. So it would take Dawn at full throttle 4 days to accelerate from 0 to 60 miles per hour. It doesn't exactly evoke the concept of a hot rod. But instead of thrusting for 4 days, if you thrust for a week or a month or a year, or as Dawn now has for 5 years, or as Dawn ultimately will over the rest of its mission, a total of 5.5 years, you can achieve fantastically high velocity. And so this is what I like to call acceleration with patience. And if you're patient, and I'm a very patient guy, this is a great way to explore the solar system. And so Dawn has changed its own velocity by far, far more than any spacecraft in history has under its own power. And we still have more to go. In fact, it's as of today, it's exceeded 23,000 miles per hour. That's significantly more than it takes to get from the surface of Earth into Earth orbit. And that's always done with multi-stage big rockets, right? But this has been done just by Dawn, just with its ion propulsion system. And this is really the key to what allows us to undertake such an ambitious mission. Now, I told you the idea for ion propulsion has been around for a long time. It's been in science fiction for many decades. Unfortunately, again, because of the constraints of time, I don't have time to tell you the entire history of ion propulsion, but I can tell you it has been around a long time. But the first mission really to use it to go someplace was Deep Space One, which you heard from Marc in the introduction, which NASA and JPL launched in 1998. And its purpose was to test ion propulsion and other advanced technologies in order to pave the way for more ambitious missions like Dawn, to check out these risky technologies to determine whether or not they really could work. And so DS1 did indeed test ion propulsion and showed that it could work, so we could undertake a mission like Dawn. And then when DS1 completed its 11-month technology mission in the solar system, we had this healthy spacecraft out there far from Earth. We proposed to NASA headquarters to undertake a so-called extended mission, that is a new assignment for it, which they approved. And DS1 went on and took what at the time were the best pictures ever taken of the nucleus of a comet. But you may not have heard much about that because we did that in September 2001 when the world's news was focused on other topics. But what matters for the Dawn story is the testing of ion propulsion. And I just want to show you an artist's concept of Deep Space One, DS1, doing that. So here it is, just after it's separated from the rocket, extending its solar arrays to produce electrical power from the sun, then leaving the moon and the Earth behind. And once we got the spacecraft in space and checked out, we turned on the ion propulsion system and ended up operating it for a combined time of almost 2 years, achieving what, until Dawn, was the record for the greatest propulsive change in velocity of any spacecraft. And that proved that we could undertake the Dawn mission. But before I leave DS1 behind, I just want to show you my favorite picture of the spacecraft. And that's here. This picture was taken when DS1 was 9 times farther away from Earth than the moon is. This is one of the greatest distances at which a human-made object has been photographed from Earth. And this picture was taken by the famous 200-inch telescope on Palomar Mountain, not too far from here. And as you know, when big telescopes take pictures of the stars, the telescope has to turn in order to compensate for the rotation of Earth. Right? That's what gives the stars their nice symmetrical shape here. Well, this doesn't tell you anything about DS1's shape. Rather, it tells you that during the long exposure, DS1 had its own independent motion through the solar system. And again, I worked very closely with the spacecraft. I spent a lot of time with it in the clean room, again, not too far from here. But this is my favorite picture of it, because what this shows me is we have a spacecraft out among the stars. And I think that is really cool. And at the time this picture was taken, DS1 was, for you astronomers or amateur astronomers, visual magnitude 22.5. And for the rest of us, what that means is it was 4 million times fainter than you can see with your naked eye. Indeed, even this star is many hundreds of times fainter than you can see with your naked eye. So that's DS1, but let's get back to what really matters here, and that's Dawn. Here it is in an artist's concept. And the first thing you notice is it's dominated by these huge solar arrays. The solar arrays, of course, convert the light of the sun into electricity, and the solar arrays have to be so big for a couple of reasons. One is we're going far from the sun. The sun is faint. So we need a large area of solar arrays to capture enough light to produce electrical power to run all of the systems. And those ion engines are power hungry. It takes a lot of electrical power to ionize and accelerate that xenon. And in fact, when we launched Dawn in 2007, this was the greatest tip-to-tip wingspan of any NASA interplanetary spacecraft. 65 feet. From tip to tip. That's the distance roughly from a pitcher's mound to home plate in a professional baseball field. And for those of you here in the auditorium, if this spacecraft, full size, were in this room with one solar array over in that corner of the room, the other would go all the way to that spacecraft model in that far corner. And for those of you looking at this on the web and the internet, it'd be big. So again, for scale, this is our main antenna. It's 5 feet in diameter. This, of course, is how we communicate with the spacecraft. And this is one of our ion engines. Here's another ion engine here. And oh boy, there's a third ion engine. So we actually do the Star Wars TIE fighters one better. So that's an artist's concept of the spacecraft. Here it is when it was on Earth being built in a clean room. And this is one of those solar array wings. This is another. And of course, they're folded up for launch because you can't fit a 65-foot wide spacecraft in the nose cone of a rocket. And these are some of our sensors, scientific instruments, that we use for teasing out the secrets of Vesta and Ceres. And this is one of our ion engines. This 1-foot diameter metal grid here has 15,000 little holes in it through which we shoot the xenon ions. And the xenon is stored in a tank inside the main spacecraft structure in here, in a tank about this big. We launched with 937 pounds of xenon. And since I keep mentioning xenon, I actually thought I ought to show you a photograph of xenon. So this is a photograph of xenon. Actually, this is my chameleon named Xenon, but because of his color, he has kind of a cosmetic affection for xenon. And to tell you the truth, he gets a kick out of being included in my public presentations. And so when I go home tonight and not only tell him a whole bunch of people at Von Kármán Auditorium saw him, but people on the web actually are continuing to look at him, he's going to think that was really cool. But back to the spacecraft. So here's another view of the spacecraft. So this is the main spacecraft structure here with various different kinds of systems on top here. This is that 5-foot diameter main antenna. This is Tom. And this is one of the 2 solar array wings. Each individual wing at 27 feet is the width of a singles tennis court. This is a very large spacecraft. And I don't know about you, but I think spacecraft are neat to look at. Right? They're neat things. They're cool. But to me, neater than what spacecraft look like is what spacecraft do. And so I'd like to spend a moment talking about what spacecraft do, because we use them to go far from home. This, of course, is home. And to the accuracy I can do PowerPoint, this is low Earth orbit to scale. It's not very far away. And this is where many spacecraft, including the International Space Station, the Space Shuttle when it was flying, and many other spacecraft live. This and somewhat higher. But it's not very far from Earth. In fact, it's comparable to the distance from here to, say, Santa Barbara. It's space, to be sure, but it's not very far away. So with that in mind, let's zoom out a little bit and introduce what's called geosynchronous orbit. And in geosynchronous orbit, a spacecraft takes 24 hours to orbit Earth once. And so if here we have a spacecraft going around in 24 hours, and at the same time Earth is rotating in 24 hours, that spacecraft always seems to be at the same place in the sky, which is why this is a good place for weather satellites, communication satellites, and others that you want either to have a fixed view of the surface of Earth, or from Earth you want to appear to be at the same place in the sky the whole time. And at 22,300 miles, geosynchronous orbit is very far away. Right? That is a long distance. It's far away even compared to the diameter of our planet. Geosynchronous orbit is far away. And in the 57 years or so of sending missions into space, the absolutely overwhelming majority of spacecraft have gone to somewhere between geosynchronous orbit and low Earth orbit. So now with that in mind, let's bring Earth down here, bring back in geosynchronous orbit, and now I'll bring in the moon and put the moon up here where it belongs at the same scale. The moon is really far away. The moon is 250,000 miles away. It's 10 times the distance to geosynchronous orbit. The moon is 30 times Earth's diameter away. The moon is really far. And as you know, or at least as we hear, in the late 1960s and early 1970s, 24 men traveled the distance from the Earth to the moon, right? People don't do that today. People don't do that. People go somewhat farther than the distance from here to Santa Barbara, but not a whole lot. But at one time in the distant past, when our ancestors were alive, people did that. And so what this shows us is the entire range of firsthand, personal human experience throughout all of human history is contained in a space of this size. And Dawn passed the orbit of the moon the day after it launched. So we launched on September 27th, 2007, and on September 28th, we had the moon in our rearview mirror. So now let's introduce the next scale, which is the Earth's orbit around the sun. And of course, as the Earth goes around the sun, it takes the moon with it. So let's bring the sun into this picture. This is the sun. And on the scale of the sun, this is the orbit of the moon. And to the same scale, this is the size of the Earth. The sun is about 109 times the diameter of the Earth. The sun is large even compared to the orbit of the moon. The entire range of firsthand personal human experience throughout all of human history is easily lost inside the sun. The sun is 865,000 miles in diameter. I mean, from this, we can conclude the sun is big. Okay, so now with this context, let me get rid of that stuff, and I'm going to put the sun down here in the corner, and up here I'm going to bring back in the orbit of the Earth. I'm magnifying it just for a moment so you can see the blue, but remember, the blue is the orbit of the moon. It just barely shows up. Earth, of course, is much, much too small to be seen on this scale, but there's the orbit of the Earth with the orbit of the moon there. There's the sun. Well, gosh, just this past August, Dawn was 3 times as far as the sun. And in just a little over a year, it's going to be 4 times as far as the sun. More than 1,600 times farther from Earth than the moon is. It's already more than 1.3 million times farther from Earth than the International Space Station is. This, to me, I'll be perfectly honest, I think this is really amazing. This is really incredible. And corny as it sounds, and I know it does sound corny, on this mission and others that I've worked on, when the spacecraft has gone on the far side of the sun, I've gone outside and put my thumb up and blocked out the sun and thought, gosh, we have a spacecraft on the far side of the sun. This is the same sun that's shone down on our planet for 4.5 billion years. And this is the same sun that's the source of virtually all of the energy our planet has ever had and will ever have. And this is the same sun that has so dominated human thought and art, literature, culture, philosophy, science, mythology, and religion throughout all of human history. And this is the same sun that's the gravitational master of the solar system. And this is the same sun that's our signpost in the Milky Way galaxy. This is the same sun that's 1/3 of a million times the mass of Earth. And yet we have spacecraft farther away than that. And when I say we, I don't mean me. I don't mean the Dawn team, many of whom are here. I don't mean the entire engineering and science community. I mean we, humankind. I mean, to me, this mission, like others, including some of the spacecraft around here, I think of these genuinely as Earth's robotic ambassadors to the cosmos, an emissary to distant worlds. And I think this is really amazing. I think everybody who's ever looked at the night sky and wondered what's up there, anybody who's has any curiosity about the nature of nature, I mean, anybody who wonders how we fit in to the cosmos, anybody who even just feels that burning passion for adventure and the sort of noble spirit of exploration, I think everybody participates in a mission like that, like this. And that is what I think is the neatest thing about a mission like that. And I hope you feel that too, because again, I think these are truly missions of humankind. And so that raises the question then, how do we do this? Well, we start by putting the spacecraft on top of a huge bomb and hoping that we have a nice, smooth launch. And in fact, we did. Dawn launched from Cape Canaveral in September 2007. And in fact, it launched just about dawn. I don't know how well you can see it in the picture here, but there's the sun rising in the background. And we had a really beautiful launch, got the mission off to a nice start. And then we can use this to follow along in the mission. So this, again, is the conventional view looking down, if you will, on the solar system. So here's the sun in the center. Here's the orbit of Earth. And this is where Earth was when we launched in September 2007. And as we follow the trajectory along, if you care, and it's fine if you don't, when it's this nice sort of chameleon xenon color, here is when we're thrusting, and where it's dark is where we were mostly coasting. So we launched and coasted for a while as we checked out the spacecraft and did some tests with the ion propulsion system and other tests before we got into here a regular long-term pattern of thrusting most of the time. And then we had a 7-month-long coast period during which we flew by Mars to, again, help propel the spacecraft further into the solar system. And then the spacecraft continued spiraling outward from the sun. You can see just climbing, I think of it as sort of climbing a solar system hill, at the bottom of which is the sun. Earth is partway up. We continued climbing up until July 2011 when we got to Vesta, went into orbit around it, and then we spent the next 14 months orbiting it as Vesta circled the sun. Then we used that ion propulsion system again to climb away from Vesta. And now we are on this long climb through the asteroid belt here. And as we're going on the way, we can zoom in and see where dawn is today. And so that's where it is on December 4th, 2014. And on the scale of this picture, Ceres looks like it's in just about the same place. In fact, today, the distance between dawn and Ceres is only about 3 times the distance between Earth and the Moon. So it's getting very close, and it's obviously only going to be getting closer and closer in coming weeks. And as long as we're zooming in, we can see where Vesta is. Dawn orbited Vesta for more than a year, but now it's farther away from Vesta than Earth is from the sun. And as long as we're zooming in, we could see, in fact, this is where Earth is. In fact, this is actually the building that we're in right now. So when you drove in a little while ago, you went under that guard gate there, and you parked here, and you can actually see in the picture, one of you, I think it was you, left your lights on. There's the traffic circle that you walk by. But anyway, so that's where we are. And we can just take a moment here to get rid of this and note something interesting. That is, today, if you drew a line from Earth to the spacecraft, it would go very close to the sun, very close. And in fact, the spacecraft is now getting so close to the sun that you too, this coming week, so please remember this, Monday through Thursday of next week, you also can block out the sun and you'll be covering the Dawn spacecraft. Now I should warn you, just have to be responsible here. I'm a professional when I do this. When you do it, it doesn't work if it's cloudy, okay? But if it's clear, the first part of next week, you can go out and block out the sun, and you will be covering the Dawn spacecraft. I think that's a pretty cool thing to do. So I think you should do that. But anyway, then spacecraft will continue on. We will go into orbit in March and undertake the same kind of ambitious, thorough, comprehensive, extensive, and I think exciting exploration of Ceres that we did of Vesta, and will reveal a lot. But you know, when you look at a picture like this, it's flat and it's static. And it's easy to forget that the solar system is different. The solar system is in motion. And in fact, the way I think of it, the solar system has this big, beautiful, complex choreography. But you can't see that here. So let's take a look at it. We're going to take a look at an animation, but I just want to get us oriented first. So we're starting with everything's location in March of 2007. Once again, the sun in the center. This is the orbit of Earth. Here's the orbit of Mars. This is the orbit of Vesta. And this is Ceres. So we didn't launch until September of 2007, but you'll see as we go around, Earth, of course, goes around once per year. Vesta is going to make 2 revolutions before we get there, and Ceres is going to go around more than 1.5 times before we get to it. So here's Earth, and as we get to September, there's the spacecraft leaving it behind, thrusting with its ion propulsion system. We're now aiming for Mars. We're going to get there. Vesta and Ceres have a long way to go. There we just flew by Mars. We turn on the ion propulsion again. We're aiming for Vesta, but we're not going to get there until way down here. Ceres down here still has another full revolution to make. But all of this choreography is worked out, and each participant executes it perfectly. Now we're in orbit around Vesta. We spent 14 months there. Then after we're finished, we turn on the ion propulsion system again. We're climbing away, heading for Ceres. But it's a long, arduous climb through the asteroid belt to get to Ceres. And as we're coming down, moving our perspective so we're closer to the plane in which the planets orbit, there we get into orbit, you can also see that relative to the plane of Earth's orbit, the orbit of Vesta and Ceres are tipped. And part of what's difficult about getting to these distant bodies, the most difficult thing is just simply orbiting, it's very complex, but the most difficult part is orbiting 2 different extraterrestrial destinations, but also tipping the plane of Dawn's orbit is also very, very arduous. But that gives you sort of the long-term view of the mission, and that's the idea of our exploration of Vesta. Here again is that south polar crater. And now we're on the verge of getting to Ceres, and that's sort of the broad overview of the mission. Now, I can tell you that we're very busy. There are things going on all the time. It's very, very complex. I'm not going to bore you with every imaginable detail of what's going on. Instead, I will just thank you very much for your attention. I appreciate you letting me tell you about the Dawn mission. I will also encourage you, if you are interested in the mission, and how could you possibly not be, you might want to visit our website, dawn.jpl.nasa.gov. You can see all our pictures of Vesta. You can see the pictures of Ceres. And in fact, as they're coming in, you'll be able to see them on the web and lots of other information about the mission. I write a monthly blog there called the Dawn Journal that if you're interested, you can follow the mission that way as well. But a lot of cool things there. So that's the presentation, and I think we have time for questions. So if you're in the room and would like to ask a question, you're invited to go to the microphone there, and I'll be happy to take them until the rent expires. And yeah, for the rest of the people, don't feel uncomfortable about leaving. I know you've been sitting for a long time. So yes, sir.
Well, first, there actually were 8 spacecraft that did orbit 2 bodies long before Dawn. They were called Apollo.
No, what I said carefully every time was extraterrestrial destinations, right? Apollo orbited Earth and the Moon.
And the Moon, yes.
You're absolutely right. But in fact, even before that, Mariner 9, for example,
Yep.
or that wasn't before that, but I mean, Luna missions orbited Earth and the Sun. But those were not destinations. It's a very different problem. It's very different. It's much, much more difficult.
Yeah, it was just a bit of levity to be injected. The real question is, how long did you have to decelerate to get into orbit around Vesta, and how long do you have to decelerate to get into orbit around Ceres?
Well, the answer to that is a little bit complicated because our notion, it's a good question, our notion of getting into orbit around these bodies is influenced by our collective thinking about how spacecraft go into orbit around other solar system bodies. So what they do is, here's the solar system body, the spacecraft comes screaming up and then executes a quick short maneuver and breaks into orbit. But that's not how Dawn does it. Instead, we spend years gradually reshaping the spacecraft's orbit around the sun. And that's why I mentioned when we're going toward Vesta and Ceres, we're spiraling outward. So we spend the entire time that we're thrusting gradually making the spacecraft's orbit more and more and more like that of its destination. So there isn't a regular sort of a transition in phase from accelerating to decelerating. It's constantly sort of sculpting the orbit to make it look more and more like that of its destination until you get up close to it, and it just takes the most gentle nudge, which of course is all the ion propulsion system can deliver, to gently slip into orbit. And in fact, when Dawn went into orbit around Vesta, it was approaching Vesta at only 55 miles per hour, slower than most of us drove here today. So that's the short answer, or medium-length answer to that question. Yes, sir.
Thanks for coming. And I
Thank
had
you
a
for
question
coming.
with I mean, obviously most of all our planets and a lot of the satellites and stuff are all in the ecliptic. Are all in the
ecliptic,
same
right.
plane.
Right.
Ceres and Vesta a little bit skewed in there, but most of the bodies stay in that. Is that, according to the theory of how we know what we think planets form, is that always going to be the case, or has Kepler found any place where there are planets maybe in orbits at all kinds of angles, or does it always have to kind of spread out into that giant plane?
Yeah, it doesn't always have to be in that plane. We used to think that it did, and the reason for that is, again, you have this large interstellar cloud of gas and dust, and as it collapses, it rotates just as an ice skater, it rotates faster and faster, just as an ice skater pulling his or her arms in spins faster, and so things all tend to be moving in the same direction. And that still seems generally to be the case. However, exceptions are now starting to be discovered, if not yet completely understood. There are several possible explanations for why that may not be the case. One could be, there are many, or several anyway, but one could be that they may start out in one plane and yet have gravitational interactions among the planets then that could distort their orbits and tilt them and make other changes. And I'd be happy to talk to you more about that afterwards.
Thank you.
You're welcome.
What's going to happen with the Dawn spacecraft after this next orbit?
Okay, the question was, what's going to happen to Dawn essentially when we're finished exploring Ceres, right? Well, it's going to stay in orbit around Ceres effectively indefinitely. That is, it will, just as the Earth stays in orbit around the Sun, the Moon stays in orbit around the Earth. You don't need propulsion to stay in orbit. And in fact, because Ceres may have an inventory of water, there may be sources of energy. I mean, there's sunlight falling on it, dim though it is. There may be some internal heat sources, perhaps radioactive materials that have been decaying over the lifetime of the solar system. So there's energy. There may be organic materials. So Ceres may have some of the ingredients that are necessary for the formation of life, which is not to say that there's life there, although a small minority of scientists would consider that possibility, but rather, more importantly, that it reflects chemistry that may be interesting to study for learning more about how life did come about in other places, so-called prebiotic chemistry. And so as responsible citizens of the solar system, we don't want to contaminate that pristine environment with our organically dirty spacecraft. And so we have chosen a final orbit for Dawn around Ceres to ensure that even over very, very long times, the spacecraft won't even accidentally reach the surface because we want to protect it. So the way I think of it is Dawn is just going to, when it's finished, when we've extracted everything that we can from it, it's going to become basically an inert monument to human creativity and ingenuity out there in the solar system.
Thanks.
You're welcome.
I have two questions. One is the gentleman who introduced you mentioned something about how you communicate and that you developed a laser system for communicating with the satellites.
Okay, well, what he referred to is that I, in different work at JPL, was involved in working on replacing radio communications for interplanetary spacecraft with lasers. But that's not yet ready for operational use. It's still experimental, although there's been laser communications now between unmanned robotic spacecraft at the Moon and Earth, but not for nearly these kind of distances. So we use conventional, in some sense, radio.
And then
Is that answering your question?
Yeah, absolutely.
Okay.
And then my other question is probably going to be really naive, but whenever I thought of things going to planets, I always thought they would go straight, not in these circles, concentric circles. And so what's the primary reason that they don't go straight?
Okay, that's a good question. I think it's entirely reasonable, right? Normally, if you want to go from here to here, you would follow a straight line. The reason that they don't, indeed can't, is because you, Lincoln, and I, are on Earth, which is already going around the sun at very high speed, more than 66,000 miles per hour. And so when a spacecraft goes out into the solar system, it's starting from there. It's already going around the sun at very high speed. I shouldn't be doing this. I should be showing you this. Or from your perspective, I guess, it's doing this. It's going at very high speed. And so you can't just stop that 66,000 mile per hour motion in one direction and go in another direction. Right? So you can think of this as if you're driving your car on the freeway at 70 miles an hour. If you just all of a sudden wanted to make a sharp left turn, you would have to stop all of that forward momentum and then turn and then accelerate. Well, spacecraft can't do that. We don't have the capability. I mean, even Dawn, with its uniquely capable ion propulsion system, can't cancel out that forward motion. And so it starts out with that motion and then builds on that, uses it. Does that make sense?
Absolutely. Thank you.
Good.
Yeah.
Hi, thank you. I have two questions. First, it was very interesting how you showed the propulsion of ion engines and how fast it travels. Very interesting how you showed it. Now, if you let the craft go out into the interstellar space, just like Voyager, I want to compare the two technologies. Will this thing surpass Voyager faster, or is the technology not comparable?
It's not directly comparable for this reason. Voyager didn't use a significant amount of propulsion on the spacecraft. Voyager, which I should point out, except for the people on the web, is right there. I think one of truly the most amazing accomplishments of humankind. It used a big rocket to push it hard, but the greatest source of the acceleration, if you will, for Voyager was the robbing this gravitational or this orbital energy from Jupiter and Saturn and Uranus and Neptune for Voyager 2 and Jupiter and Saturn for Voyager 1. So it's entirely different. That doesn't have anything to do with whether it uses ion propulsion or conventional chemical propulsion. That is, the brilliance of the trajectory designers at JPL was to send it on a course where it could extract that energy from those bodies in order to travel out of the solar system. Now, Dawn, we didn't want to go out of the solar system. We wanted to go to Vesta and then to Ceres. So we weren't trying to do that. So we used a smaller rocket, and we did take, as you saw, some of the energy from Mars. But the rest of it is the maneuvering that's done by Dawn to go into orbit, maneuver in orbit, get out of orbit. That's the technological benefit of the ion propulsion, which is just entirely separate from these gravity boosts. And there isn't any reason you couldn't combine them, but they're simply different. I don't know, does that answer your question?
I just wondering if you let Dawn just go out, I was wondering if it would catch up faster and would surpass Voyager. That's what.
Dawn itself would not be able to because the boost that Voyager got from the planets was more than Dawn's ion propulsion system could deliver.
So do we have a technology right now that we can go and catch up with Voyager and go faster?
If that were the sole objective,
Yes.
we could indeed go faster. In fact, there is a spacecraft that's traveling out from the sun faster than the Voyager spacecraft. It's called New Horizons, and it's going to get to Pluto. It's going to fly by Pluto in the middle of July because it started with a bigger rocket, and it went on a trajectory that took great advantage of Jupiter's gravity with the objective of going out faster because they wanted to get to Pluto. Again, that wasn't even Voyager's objective. Voyager didn't rob Jupiter of its gravity in order to leave the solar system. I said gravity, I meant it didn't rob it of its orbital energy around the sun, I misspoke. It was targeted for Saturn. So none of these spacecraft has specifically been focused on simply going far as fast as you can. And if that were our objective, we could do that faster.
Okay. Now the second,
Oh, go ahead.
second question, I keep hearing about the orb cloud, the Kepler belt, and the asteroid belt.
Mm-hmm.
And I read it, I don't know if these terms are used interchangeably, or are they actually three different belts?
They're
of
entirely
asteroid?
separate.
Okay, so
and-
can you orient me, like where, and how it
Yeah,
is?
so I'll just give you the short answer, and we can talk about this
Yeah.
more afterwards. So the Oort cloud is I'll take them in the order in which you mentioned, is the farthest from the sun. And it may extend out to a light year or something of that scale, maybe even more. So it is very, very far. We've never had spacecraft even remotely that far. Even the Voyager spacecraft are nowhere near that far from the sun. They're very close on the scale of the Oort cloud. The next one in, I think you may have just misspoken, and that's fine. It's called the Kuiper belt, not Kepler. Kepler
Yeah,
was
right, yeah.
two different astronomers. So that's outside the orbit of Neptune, and Pluto and many other bodies that maybe you've heard of are there. And then the asteroid belt is this region between Mars and Jupiter.
Okay, great.
So there are three different groups of objects.
Thank you.
You're welcome.
My question is sort of about the future, so it's not something you
About
can,
future
you can
what?
answer about the future, so you can't answer it precisely, but I just want your opinion.
If I wait, I could, right?
Yeah. So the solar-powered ion engine is great as long as you have enough solar power, but the further you get out from the sun, the weaker that is, of course.
Exactly.
And so I've been hoping that someday we could maybe develop a lightweight nuclear power source that would be more powerful than even a large solar array.
Mm-hmm.
And I'm kind of been disappointed. I haven't seen much progress in that area, and I was hoping you could predict when we might do something like that.
Okay, well, I'm not sure how well I can predict it, but I can at least say that NASA greatly appreciates the same thing. And just so to clarify it, it's that as it is, dawn with these huge solar arrays is going to about 3 times Earth's distance from the sun. So you're absolutely correct. I mean, everything you said is quite correct, that if you want to go farther with solar-powered ion propulsion, you would need either impractically large solar arrays, and of course, larger solar arrays weigh more, or more to the point, they have more mass. That's mass that you have to propel through the solar system, and it's complex and expensive. And so there was a committee of the National Academy of Sciences and National Research Council a few years ago that recommended a high priority for technology development is precisely what you said, which is essentially the marriage of high efficiency nuclear power sources with this ion propulsion. And there has indeed been work on that, but you personally, I don't know you, but you personally and I as taxpayers only allocate a very small amount of money to NASA, like 0.5% of the federal budget. It's not very much. In fact, your contribution to NASA today is this 15 cents. It's a very small amount, and NASA simply can't do everything. So we appreciate and recognize the importance of this development for enabling missions to more distant destinations in the solar system that are otherwise unreachable. But NASA has a great deal of fascinating work to do, and it can't do everything all at once. So for your real question of can I predict when it will happen, the short answer is no, I can't, but I would think that certainly in the professional lifetime of many people in this room, it very likely will happen.
Thank you.
Sorry for a wordy answer.
Earlier on in the talk, you showed a graphic which represented the asteroid belt with all the little, you said 10,000 or however many asteroids, and then they were between the orbits of Mars and Jupiter. But then it also seemed to show 2 other clumps of asteroids that seem to be right over the orbit of Jupiter.
Right.
Does Jupiter go through these fields of, how does that work?
Okay. Yeah, so you're quite right. There was a sort of cloud of asteroids. If you were referencing it from the sun, about 60 degrees ahead of Jupiter in its orbit, and about 60 degrees behind. And Jupiter doesn't plow through them because...
So they're all traveling together?
Exactly. They are orbiting, all of those bodies are orbiting the sun from your point of view like this. And so some of them lead Jupiter in its orbit, some of them follow Jupiter in its orbit. And in brief, it turns out that there are, for bodies in orbit like that, there are these regions that are somewhat stable. And so if an object happens to happen into one of those places, it can sort of be trapped in this orbit leading or following Jupiter. And there are such places in all sorts of orbits. So with the moon going around the Earth even, there are places leading the moon in its orbit and following it that are similarly sort of stable as there are for Earth going around the sun. And astronomers have looked for bodies in these places, but they're small and difficult to find. One, I believe, is known already for the same sort of location for Earth going around the sun, and undoubtedly there are more, and astronomers will continue to look for them. And sometimes spacecraft can take advantage of similar sorts of gravitationally somewhat stable points.
But in these clumps, some of the objects would be closer to the sun, and wouldn't they be traveling faster in their orbits than the ones that are a little further out? Wouldn't they eventually then, all these clumps fall apart?
Well, yeah, it's not the ideal system that I just described. It's more complicated for the reason you said. There are also gravitational, the gravitational influence of all the other planets makes it still more complicated. And so it certainly is not the case that every one of those objects is always in that orbit. They may sometimes get trapped there for some amount of time, but not indefinitely. So some of them may occasionally come and go. But, and the fact that the Jupiter and for the Earth-Moon system and these others, the orbits aren't circular also makes it more complicated. But the objects that are there are less subject to being, to having their orbits disturbed and being moved elsewhere. It's almost as if Jupiter sort of helps keep things there for longer than they otherwise might be.
Thank you.
And,
Hi, good morning, sir. I just want to ask you, I read something on, I believe it's the NASA's website the other day around Thanksgiving. And can you kind of explain the article or something published on the 26th by NASA and by one of the Nature magazines on the 27th that says, I think it has something to do with the radiation belts around the Earth and also the plasmasphere? They found out something new?
I don't want to take a lot of time for that here, although I'd be happy to talk with you afterwards. What you're referring to is there are radiation zones around Earth called the Van Allen belts, discovered by James Van Allen using a spacecraft that was developed here at JPL, the United States' first spacecraft to orbit Earth. So there are these NASA spacecraft called the Van Allen probes, which are specifically designed to be studying these radiation belts around Earth. And we have had a gradually evolving understanding of the complexity of these radiation belts. They're often just depicted as, a belt surrounding Earth. But what the Van Allen probes are showing is that these Van Allen radiation belts are much more dynamic, and that sometimes even the number of these radiation belts changes, and that there are very, very, very high velocity particles, subatomic charged particles, moving around in these belts that show that it's much, much more dynamic than had previously been appreciated. And I'd be happy to talk with you afterwards about that, but because it's so different from the dawn topic, probably not appropriate use of time. Okay. So here are some questions that came in from the outside world. What color is Vesta to the eye? Would it be gray? It would be, that's a good question, because as I told you, and as you're seeing there, it's shown in black and white. It would be, I'm not very good with colors, but it's a little bit browner than gray. How's that for somebody who's not good with color? But, you know, when you look at, I mean, in many ways, Vesta is somewhat similar to the moon in appearance. So it would largely be gray, but it does have a little bit more of this sort of brown tinge. Is that a good word? I don't know. Carol, can you help me with the color? Okay. Let's see, the next one, with respect to ion propulsion, what makes ions more efficient? Why ions instead of regular particles? Okay, the reason we use ions is only that the ion is a charged particle, has an electric charge. Just like, you know, you can give your hair an electric charge, static charge, with the, you know, a balloon, things like that. You know, comb, how your hair sticks up. So it's the electrical property that we're taking advantage of. When it has the electric charge, we can accelerate it with a voltage. That's why we use ions, because the voltage quickly accelerates these particles to this fantastically high speed of 90,000 miles per hour. So I hope that answers that question. And the next one is, how do you link a meteorite to Vesta or another body? And there are several ways to do that. The initial connection between the Vesta meteorites and Vesta was made by astronomers in about 1970 when they used an infrared spectrum. So infrared, of course, is a wavelength of light that we can't see, just like there are wavelengths of sound you can't hear, but the dogs can hear. So this is beyond what we can see with our eyes. And a spectrum is when you break the light up with a prism. And as you know, when you break up white light with a prism, it breaks into its constituent colors. You get all the colors of the rainbow. You can do the same thing in the infrared, see effectively the constituent colors. But what's neat about that is that light carries a fingerprint of the material it reflected from. So if you look at each color very carefully, they're not all of the same intensity. They vary. And that is a unique signature. So when astronomers applied this to studying Vesta, they discovered that the infrared spectrum of Vesta provided an excellent match for these meteorites that they had in the laboratory. Then there was additional data from Dawn that really clinched the story. From other places like Mars, the reason, or the way that connection was made is NASA landed spacecraft on Mars in the 1970s, the Viking spacecraft, that measured the composition of the Martian atmosphere, thin though it is. And then they were able to determine that some meteorites had the same gases trapped in them. When they were liberated in laboratories, they saw that this is the atmosphere of Mars coming out of this rock. And so this rock must have come from Mars. And of course, we have samples from the moon, and so we know enough about the moon to be able to recognize samples when they're found on Earth. There are other ways to do it and other lines of evidence as well, but I hope that answers that question. And so, thank you again for your interest.